presentation.
Okay. Good morning.
Can everyone see my presentation?
Not yet, but it's coming. Yeah.
Yes, we can see.
You can see. Let me. Okay. Let me just do so I can see myself, because otherwise it's a little bit awkward. Yeah. Okay. So welcome everyone. Thank you again for having me and for allowing me to talk to you guys. So for those of you who were here last week, we talked about the laws of nature and what happens when you break them. And today we will continue our discussion into this. Wait. For some reason, I cannot see myself. So let me try and show video panel. Okay. So now this should be okay. Okay. So can you guys see me?
Yeah, I can see you.
You can see me. Okay, very well. Now I can see everyone. So I want to start today. I would like not to waste time with introductions, but to already start our discussion. But of course, I want to summarize a little bit what we talked about last week, because, I forget. I'm old and not so wise, so I forget things. So I want to organize our thoughts about what we talked about last time. So we started last time talking about what is a mathematical law and what is a mathematical truth. And then we started talking about physics, and we talked about what is the physical truth and what is a physical law. And we saw that mathematics and physics are essentially very, very different. Why? Because in mathematics, the truth is any statement that follows from the axioms. You have an axiom, let me remind you, it's a statement which we take to be true without having to prove it, right? And we gave a few examples of axioms. One is that between every 2 points, there is one straight line. Or, for example, in the first axiom of logic, if A equals C and B equals C, then A equals B. This, of course, cannot be proven. We just take it to be correct, and we ask what are the things that would follow out of that. And everything that follows out of that, we call it true. And that's a very nice thing, because that gives mathematics a very powerful makes mathematics a very powerful concept, especially in a world where truth is scarce. It's very hard to find something which is really true. In physics, things are different. In physics, any statement which is corroborated by observation is true. So the only thing that is true in physics is the observation. So the truth is that if I take this marker and I let go, it will fall down, right? The law of gravity is not truth. The truth is just that this pen falls down. That's a big difference. And then we said that physical truth becomes a law of nature, right? Only after some statement about the origin of phenomena has been deduced by many independent observations, which does not arise from another principle. It's the lowest principle possible. It allows us to predict the outcomes of experiments. Otherwise, it's not useful. It's not part of physics. Many objective attempts to prove it have failed, so much that all the people working on it, all the community of physicists agree that this is a law of nature. So the fact that this pen falls down is true. But the law of nature is that any mass is repelled or attracted to any other mass with the law with Newton's law of mass action. So the multiplication of the mass times constant divided by the distance squared. That's a physical law. Why? Because we cannot disprove it by experiment. We just didn't find the situation where we disprove it. And although that sounds really strange, physical laws have been broken again and again over the years. And this is what we did yesterday. We started talking about how physical laws have been broken. And I want to start now talking about a little bit about how science works. And this has been thought, or this kind of formalism of how science works is due to the philosopher Thomas Kuhn, who lived in the 1960s in the US, in the United States. And he said something like this. And I'm showing you this because this is a demonstration of what we talked about. So Thomas Kuhn suggests that any scientific method has several stages. The first stage is what we call pre-science. This is the situation that no one knows anything, right? These are the ancient people of Europe or Greece or whatever. And then they form something which we call a paradigm. What is a paradigm? A paradigm is a set of natural laws that explain the observations. And then there is normal science. Normal science is the situation that happens typically where many people, many scientists work around, look at things, and try to explain them from the paradigms. For example, the first paradigm of Aristotle was that the perfect motion or the natural motion was circular motion. Remember that? He saw, the observation was, the sun rises up on the east and sets down on the west. The moon rises and sets around the earth. So that kind of makes sense, right? That the natural movement is circular and everything rotates around humans, around the earth. And then people started doing normal science. What does that mean? That means collecting observation. For example, the motion of other planets or the motion of other celestial objects like comets and so on. And then there's an accumulation of problems and a crisis. What is a crisis? A crisis is the situation where there are many observations which cannot be explained with the old paradigm. And then scientists start thinking about new ways to solve the problems which go outside the paradigm. And then they reach a paradigm shift, a situation where the old thinking is abandoned and the new thinking takes place. And we've seen at least two of these examples. And then the situation repeats. The new paradigm becomes the normal science until there's an accumulation of problems, a crisis, and then a paradigm shift. So let's see how that worked for us, right? The first thing for us was Aristotle. So the natural motion is circles and the sun orbits the earth. And then during the Middle Ages, there is an accumulation of observations that the stars of Venus and Mars, they're not moving in the way they should have been moving if they move around us. And then, after quite a long time, it took more than 1,500 years, until Galileo suggests a paradigm shift. He says, no, The natural motion is circles maybe, but we are orbiting the sun. And he added, velocities add up. This is a different law, which we called Galileo's law of velocities. And then came another paradigm shift, because Newton tells us the natural motion is not circles. The natural motion is a straight line, but that follows the new law of nature, which is Newton's second law, that the action, the force that is exerted upon a body will be equal to the mass multiplied to the acceleration that body feels. So we see on and on a paradigm shift, because this was not enough. We then moved to Einstein, right? And Einstein said, well, Galileo's law of velocities is incorrect. There is an accumulation of the observations, even if the observations was only in Albert Einstein's head, because he only did thought experiments. That's still enough for him to suggest a paradigm shift. And Einstein's paradigm shift is that Galileo's law of velocities is just an approximation. It's a good one, but it's an approximation. And the real law, the real natural law, is that the velocity of light is always a constant. Now, this brings about many, many strange things, but that's still correct. And today, we want to talk about the third crisis and the third paradigm shift, which is the birth of quantum mechanics. Chaim, how long do I have?
You have time, no problem.
I have time, okay? Excellent, excellent. We're going to go slowly, and I think we're going to have fun. So let's look how Schrödinger takes Newton and how the old laws of physics, the essential laws of Newton, are broken down. So we actually start the story. We actually start the story from a very famous statement by the Baron Kelvin. Baron Kelvin was a very famous scientist of the early 20th century, late 19th century. And in a conference of the Royal Society of Nature, or the Royal Society, which is the British Society for the Natural Sciences, he said quite publicly, there is nothing new, no new discoveries to make, only make more accurate measurements. Now, why would a physicist say something as strange as that? Well, because by the time he was talking, there were two amazingly nice theories. One of them is the theory of light by the physicist James Clerk Maxwell, which formulated the equations that govern the motion of light. And those work very, very well. They explain very well the properties of light, how light moves in straight lines, what we call geometrical optics, or why if we put it through a glass triangle, it will break down to colors, or he explained the interference of light and things like that. It was very, very successful theory. Another successful theory was Kelvin's own theory of the atom, because he did experiments and he realized that to some extent you can think about the atom as a nucleus, a very heavy nucleus, and electrons, very light particles rotating around it, quite in similarity to the Earth rotating around the sun. And since we already knew the equations that are governing the laws that the Earth is rotating around the sun, that's Newton's laws plus Newton's law of gravity, that make perfect sense, that electrons around atoms move in the same way. Of course, there was one problem with this statement, and that is, for example, if you combine these theories, the world should not exist. That's kind of strange. Why would I say that? Well, that's what comes out of it. Because if you take Maxwell's theory, it predicts that if you have a rotating electrical charge, it will emit light. And when it emits light, it reduces its energy. Okay? So you have, in Kelvin's theory, electrons rotating around the nucleus. But while they are rotating, according to Maxwell's theory, they must emit light. As they emit light, they lose energy, and when something loses energy, the radius of rotation will decrease. So eventually, in every atom on Earth, the electron should collide with the nucleus. Now, luckily, that doesn't happen. But this means that these two theories are inconsistent with observation. And remember, in physics, observation is the truth, not the theory. And the observation is that indeed electrons rotate around atoms, but do not lose their energy. How can this be? We will talk about it, of course. Another amazing observation is this. You can recognize this. This is the periodic table of the elements. Now, this is quite amazing. Probably you never thought about it, but it turns out that if you look at the natural elements, they have an amazing property. And the property is that the chemistry that they do will define on how much their weight is a multiple of the hydrogen atom weight. So, if you have something which is twice the hydrogen atom 8, or 10 times, or 18 times, or 36 times the weight of the hydrogen atom, it will not do chemistry at all. These are the noble gases, helium, neon, argon, and xenon. But if you have two elements and the sum of their weights is twice or 10 or 18 or 36 times the weight of the hydrogen atom, they will do chemistry. So two hydrogen atoms will do chemistry. Lithium and fluoride will do chemistry. And all these things have to do with these magic numbers in the periodic table of the elements. Now, that's very strange. Why would material work in multiple quanta of the hydrogen atom? Why are their properties determined by multiple numbers of the hydrogen atom? Why do they appear in multiples of the hydrogen atom at all? So that's very strange, and that you cannot observe. And there are many, many other experiments which together accumulated and could not be explained using the old laws of nature, Newton's laws. So I would like to take you through them, but I would like to take a different drive. I would like to show you quantum mechanics with your own eyes. Just to see it with your own eyes. It's very easy to see. In order to do that, we need to start with an experiment with light. So to do that, we take a simple device, which is a laser pointer. It's just a flashlight that shoots a very focused beam of light. And we shoot it through a device that looks like this. This is just a piece of paper with two tiny slits on it. This is called the two-slit experiment. And you have a wall behind it. The room is dark. You'll see the laser on the wall. But as it passes through the double slit, you will see what we call interference pattern. You see, a bright region, then a dark region, then a bright region, then a dark region, so on and so on. But not only two, many of them. This is called interference. And if something interferes, we say that it behaves like a wave. Why do we do that? Because we have the experience of ocean waves, and ocean waves interfere. Let me show you. Let's say we do this experiment with water waves. So we take a big tank of water, and we put a double slit here. These are the two cracks in the wall, right? And below them, we start moving the water up and down. So as they go throughout the two slits, they will start moving up and down, and they start spreading in the water like pebbles from when we throw a stone in the water, right? They grow in circles. Now, as they start touching each other, a funny thing happens. If they touch each other in a place where one wave was at its top and the other wave was at its bottom, so the both waves were at their tops, then the combination of them would be even higher. So the sum of the waves will have a higher amplitude. We call this constructive interference. But if we look at a place here where one wave was maximal and the other wave was minimal, then the sum of the two waves will be zero. Now, as the wave is progressing, water goes up and down, but at that particular point, the sum of the two waves is always zero. So if we look at it, we see that at this point, there is no wave at all. The water are still, they're not moving up and down at all. So there is destructive interference at that point. Now, as the two waves progress towards the screen, eventually they hit the screen. Now, at the area when they hit the screen, when they are both at maximum amplitude, the water on the screen will go up and down with double the amplitude. So you will see what we call a bright light, a bright line. But in these dark areas, these are the areas where when one wave is maximal, the other is minimal, and vice versa. So in these areas, the sum of the two waves is zero, and there is no wave here. So we see this interference pattern. Now let's do this experiment with electrons. Remember, electrons are these tiny particles that rotate around the nucleus. So let's say we take an electron gun. An electron gun is simply a piece of wire which we light up, which we heat up, and electrons start leaving it. And we force them to move through a double slit. And what do we expect? Well, if these were like, Newtonian particles, if these behave like classical balls or maybe pieces of sand, grains of sand, what do we expect? We expect that if an electron moves, it either hits the wall or passes through the slits. Now, if it passes through the slits, it would continue on a straight line and hit the screen behind it. So we see two lines behind the screen that represent the two slits. That's kind of intuitive, right? Now, let's see this experiment. This is an experiment done in Hitachi labs already in 1989, and they release electrons one by one. Okay? Now, another feature of classical things like balls, grains of sand, bullets, electrons, is that when you release them, you will see them hitting the screen one by one. While if you have a wave, right, there's no point in asking this question, right? A wave just hits the screen and is continuously moving on the screen like water. So let's see. So they are releasing electrons, and everyone can see the electrons moving and hitting the screen one by one. Can you guys see it? Yes, you see the electrons hit the screen one by one. But now this experiment is done over and over and over again, many times, and something very, very strange happens. As this experiment goes on, what we see behind us is not the two lines that we were expecting, but an interference pattern. And there is quantum mechanics in front of you. This is quantum mechanics. We see the electrons hit the screen one by one, but as we do the experiment many times, we see that the accumulative result has an interference pattern. And there is no way to explain this with Newtonian mechanics. There is simply no way to do that. You're more than welcome to try. And this was the crisis that faced a whole generation of young scientists. Erwin Schrödinger is the one that we'll talk about because he introduced Schrödinger's equation. And of course, this requires explanation. And Schrödinger's explanation, which we now call quantum mechanics, is the following. As opposed to Newtonian mechanics, particles are no longer represented by the velocity and position. Rather, they are represented by something we call a wave function. What is a wave function? It's a mathematical thing. It's just a function of time and space. It obeys a new equation. It no longer obeys Newton's second law, which is a mathematical equation. It obeys a new equation, which we now call Schrödinger's equation. It looks like this. It doesn't matter how it looks like. What it does matter is that the solutions of Schrödinger's equation look like waves. It looks like ocean waves or light waves. It's kind of similar to Maxwell's equation of light. But what does this have to do with the two-slit experiment? Right? This is all kind of theoretical, maybe a little bit abstract. Well, no, there is a clear relation between this and experiment. And this is what Schrödinger told us. He told us that the relation between this and experiment is the following. The probability of finding a particle, our electron, at some point in space, which we call x, at some time in t, is given by the square of the wave function. So if we know the wave function, we know the probability of something to happen. Now, let's relate that to the two-slit experiment. What we need to do is to solve Schrödinger's equation for the electron in the two-slit. What you will find is that on the screen, the probability, the wave function, is very big in these yellow areas and very small in the dark places. Then it becomes very big and then it becomes very small, like a wave. So now, that means that the probability of an electron to hit the screen here is much larger than the probability of an electron to hit the screen here. So you do the experiment many times. And the experiment is statistical by nature. Now, if it's statistical by nature, and we'll get to that point a little bit sooner, and in a little while, then every time you release an electron, you will see it hitting the screen, but in a different place. Like every time you roll the dice, you see a different number, right? Anything between 1 and 12, and they all have their own probabilities. So every time you see the electron hitting the screen, it will come with a different probability. Now, when you do the experiment more and more and more, you will see more electrons hitting where there's more probability. And this is why you will eventually see this interference pattern. Now, this works perfectly, but it's very, very strange. Let me show you why. For example, because you cannot talk about a particle as going through the left slit and the right slit, right? I cannot ask you where, in which slit did the particle go, right? That's a question which no longer makes sense, because we are now no longer talking about a classical particle. Right? But we're not really talking about a wave either, right? Because we see the electrons hitting the screen one by one. So what are they? Are they waves? Are they particles? This is called the particle-wave duality. And this is at the base of quantum mechanics. We'll get there. We'll try to explain this a little more because we have no intuition into this thing. I want to skip this part. Okay, this is about Schrodinger's cat, but I will skip it because I have two other things that I want to talk about. So the meaning of Schrodinger's equation is double. The first thing is that Newton's laws are no longer valid. They do not work. They're not laws of nature because we find an experiment that contradicts them, right? And this was our main characterization of a physical law. You cannot have an observation which breaks down physical law. So if you have an observation which breaks that, it's no longer a physical law. But that's crazy. Think of the consequences. It changes everything we think about measurement and motion. Why? Because Newton's law and Einstein's law are deterministic. If you know where the particle started, you know where it will end. Now, this is our daily intuition, right? You take a ball, you throw it to your friend. Now, without even thinking about it, you measure the strength and the angle that you need to throw your ball because you know that if you do this, the ball will reach your friend at the end. But this is no longer correct for quantum particles. You send all the electrons under the exactly same conditions, but each one of them hits the screen at a different position. And you can only talk about the probability of something to hit somewhere. You can only talk about the probabilities. That's crazy. This is a change of the way we're thinking. That's a paradigm shift. And this, of course, is crazy. And Schrödinger answers Newton and says, don't worry. There are other laws of nature which come up from quantum mechanics, like Pauli's exclusion principle or Heisenberg's uncertainty. And we will talk about them in a while. But let me first, let's talk about Heisenberg. Oh, my God. Let me go back. This is a Heisenberg uncertainty principle, and that's a law of nature. So let's ask ourselves what that is. Heisenberg's principle of uncertainty says that some pair of quantities, like position and velocity, cannot be measured simultaneously to infinite accuracy. I will explain. So let's say you take a ball, right? And you throw it to your friend, and you look at the ball. So wherever the ball is, you can roughly say or measure where the ball is and what is its velocity, right? And there is no limit to that, right? If you have very good measurement tools, you will be able to measure the velocity and the position of the ball to whatever accuracy that you want. But that turns out not to be correct for quantum particles. If you know the position of the particle, you do not know its velocity. And if you know its velocity, you cannot know where it was. Okay? And we will, of course, connect that to something that we've seen. But let's try to understand the meaning of this law. Oh. So think about Shotabin. Remember, he's a good friend and a demonstrator, and he's holding a piece of rope. And he's doing this. And he's making a pulse in the rope. Now, can everyone tell me where the pulse is? Yes, you can tell me where the pulse is, right? Because the pulse, you can say, oh, it's roughly in the middle of this bump. That's a well-defined statement. Now, what can't you tell me? I will show you what you can't tell me. Let's say that now Shotabin is doing this. He's moving his arm up and down constantly. Up, down, making a perfect wave. So now, can you tell me where the particle is? You're going to say, this question is strange. You cannot, it doesn't mean anything to ask where a wave is. Well, it did mean a minute ago when I asked where the pulse was. But now, there is something that we know about this wave. Okay? So this was the pulse wave, which we knew exactly where it was. It was almost exactly, it was centered around this maximum. But when we look at this continuous wave, there is something that we know, and that something is something we call the wavelength. The wavelength is the distance between two consequent maxima of the wave, right? Can you know what the wavelength is? Yes, we can measure it. Let's say it's about a meter. But can you tell me what the wavelength is in this pulse? That's strange, right? There is no wavelength. It's just a pulse. So either we know the position of this wave, or we know the wavelength. And the particle wave duality and the formalism of quantum mechanics tells us that every particle is a wave, and the wavelength is associated with the velocity. So this is counterintuitive, and I'm not going to go into why this is so, but it's definitely so. It has been measured and corroborated in experiment. So if wavelength is equal velocity, you can either know wavelength or know position, but you cannot know both. Now it turns out that this is not a flaw in the measurement. It's not a flaw in your device. It's not like if you have a better ruler or a better laser pointer or something, you would be able to do that. That's a law of nature. Now, this relates to the double slit experiment where we saw a very nice interference pattern, right? So that interference pattern has a wavelength, so we can know the wavelength. What we can't know is whether or not the particle moved through the left slit or the right slit. So we have an uncertainty in the position, but we know something about the wavelength and hence the velocity of these particles. And that's a new law of nature. And let's go on to another law of nature. We're not going to go into the second one. We're going to say a little bit about this. And Einstein didn't like this theory very much. He's actually quoted in saying God does not play with dice, meaning that it cannot be that the laws of physics are not determinists. And to this, Schrödinger answered, well, what can I do? He does play with dice, right? I mean, it seems like quantum particles are not deterministic. They are statistical by nature. And then Einstein asked, maybe there are hidden variables. What do I mean by hidden variables? When we take the dice and we throw them, it looks like a statistical experiment, right? Every time you throw the dice, it will reach a different number. But it's not really statistical, but it has to do with how we move our wrists and how fast we throw our arm and so on. If we do it every time exactly the same, the dice will land exactly on the same things. But it turns out that there are no hidden variables, and this was actually proven experimentally using a set of inequalities called Bell inequalities. I will not go into this, but it turns out that as far as we know, the quantum particles are deterministic. I want to briefly go to two amazing properties of quantum mechanical particles, because this is a really strange theory. It has no intuition in our daily lives. Let's start from something called tunneling. So he's shot a beam and he's playing soccer. Now he's bumping into a brick wall and he wants to move the ball to the other side. What does he have to do, right? He has to kick the ball above the brick wall, right? There's no other way. Now, in order to do that, he has to kick the ball hard enough. He has to give the ball enough energy to go up, to resist gravity, go as high as above the brick wall, and then the ball will go around the wall to the other side, right? That's our perfect intuition. But it turns out that if the ball was a quantum mechanical object, then you don't need to give it so much energy. Because quantum mechanical objects can actually pass through walls. They can move through regions, even if they do not have the sufficient energy to do so. Why? Because they are not particles. They are wave particles. They are quantum particles. I'm not going into the mathematics, but it turns out this is a property which has been measured over and over again. And it has been measured in radioactive particle decays, has been measured in chemical reaction, has been measured in electronic devices many, many times. When we see quantum mechanics, we are going to see quantum mechanical tunneling. Now that's pretty cool, right? Things that go through walls. That's totally unintuitive. But there's another unintuitive thing, which is even crazier. This is quantization. What is quantization? Quantization is the following. Let's imagine shot a beam throwing a ball inside a room, right? Now, what are the limitations on the velocity of the ball? Well, the only limitation is how strong shot a beam is, right? And we all know that shot a beam is extremely strong, right? So if he wants to throw the ball at one velocity, or double that velocity, or triple that velocity, he can do that. There is no limit to the velocity. Even more so, the velocities are continuous, right? He can throw it at a velocity of 1 kilometer an hour, or 2 kilometers an hour, or 1.5 kilometers an hour, or 1.3 kilometers an hour. Whatever velocity he wants. The only thing he needs to do is move his arm in the correct velocity and give the ball the right velocity. However, this is a Newtonian ball. There's no limit on velocity. However, and that's very, very strange, but it's a property of the Schrödinger equation. If the ball was a quantum ball, i.e., if it obeys not Newton's equations, but Schrödinger's equation, then the velocity can have only certain values. So depending on the mass of the ball and the size of the room, ball could only be thrown at 1 kilometer an hour, and then 8 kilometers an hour, and then 16 kilometers an hour, but not in between. And if Chota would try to throw the ball in those velocities, the ball would not move. How crazy is that? How unintuitive is that? But this is, as far as we know, the laws of nature, because this is actually a consequence of a quantization, consequence of Schrödinger's equation, which is a consequence of the uncertainty relation, which is, as far as we know, a law of physics. And this makes something quite amazing. Why? Because an electron around the nucleus, and now we close the circle that we started with, an electron around the nucleus is like a quantum ball. So the nucleus is like a room in a way that pulls the electron, and the electron moves in this room, and it can only have certain velocities. Now, you know that velocity and energy are related, right? Energy is velocity squared divided by twice the mass, right? Kinetic energy. And therefore, if you have a certain set of velocities, you only have a certain set of energies which an electron can occupy. So, if we have an electron around the nucleus, it will move at a given energy. And this solves the original paradox that we talked about of how come the collision between Maxwell's law and Kelvin's model of the nucleus. And the solution is that Kelvin's model of the nucleus is a classical model. It doesn't work. Nature does not work that way. In reality, quantum particles, electrons, obey quantum mechanics. So they are not rotating around the nucleus and losing their energy, but they are stuck at a certain energy. And they cannot lose that energy because they have to go in certain energy quanta. And quanta is a measure, and this is the origin of quantum mechanics. Now, this is very, very nice. Why? Because it explains a ton of things. It explains the contradiction between Maxwell and Kelvin, but it also explains the periodic table of elements. I will not go there. But it will also explain something really amazing. Now, let's say we give an electron the exact amount of energy to go from the first energy to the second. Let's say we hit it with another electron or with a very hot nucleus. So what will happen? The electron will go back. It will lose its energy by emitting a beam of light. Now, the color of that light will depend on how much energy the electron loses when going from this level E2 to this level E1. If it's short, if it's a small energy difference, then it will emit, say, green light. But if it's a large energy difference, it will emit blue light, and so on. And now, the color depends on E1 and E2, and this depends on the specific nucleus, which means that it depends on the specific element that the electron belongs to, hydrogen or helium or lithium or barium or beryllium or carbon or whatever. Because the nucleus determines the height of these energies, and then the light emitted from those will give us the color. Therefore, we can identify elements according to their light. We look at the light, we analyze the color, and then we can say something about the elements which gives us this color. And this is kind of nice because we can now look at the sun or at very distant stars or at very distant galaxies even. And we can see the light coming from these galaxies, and we can analyze the light, and using the laws of quantum mechanics, we can interpret the signal and say what is the composition of elements in a faraway galaxy using the laws of quantum mechanics. Now, how crazy and cool is that? I think that's pretty awesome. So I think we're nearing the end. So I would like to summarize again. Again, this is a summary of the two talks. The laws of nature cannot be broken. Otherwise, they are not laws of nature. However, we can see an experiment that breaks a natural law, a physical law. But in that case, if we trust the experiment, then the experiment is okay because in physics, the experiment is the truth. What we thought was a natural law is not a law. And then we have to change our paradigm. And this happened again and again and again. And the list of natural laws that we now have is actually not that big. What are the laws of nature? Well, we have the conservation laws, the conservation of energy, momentum, charge, and so on. As far as we know, these conservation laws cannot be broken. We did not find an experiment that breaks conservation laws. We have the gravitational law, which tells us that the force, the two bodies with mass exerts upon each other is a multiplication of their masses divided by the square root, the square of the radius. We have Einstein's law of nature, the velocity of light is a constant. We have quantum mechanical laws, Pauli exclusion principles, and Heisenberg's uncertainty. And we have another law, which we did not discuss this. This is the second law of thermodynamics, which can actually be formulated in a different way. The arrow of time always moves forward. That's a cool law. It's actually very useful because it explains a lot of what we see around us. And that's it. These are the laws of nature. Now, what do physicists like me do under normal circumstances? We look at observations and we try to explain how these observations can be derived from this set of laws of nature. That's what we do. And as far as we come up with, these laws have not been broken yet. But maybe someday they will. Maybe someday. There's nothing holy or important about these laws of nature. They are just useful to us in explaining the physical reality around us. Let me finish with another law. It's not a law of nature, it's actually a law in social sciences. And I call it Dubé's law. It's not me. There is another, Dubé, my father, who wrote a very nice book. And in this book, he wrote down Dubé's law. And it tells you that the more complicated the problem is, the less you have to learn in order to have an opinion. Let me give you an example. We saw this already. This is the hydrogen atom. What is a hydrogen atom? A single electron rotating around a single nucleus, which has one proton and one neutron. That's the simplest problem in the universe, right? One electron, one nuclei, one proton and neutron. Very simple. Now, in order to understand, to say something about this problem, you have to learn. You have to learn physics, and you have to learn differential equation because you want to solve Schrodinger's equation. And then you solve it. And then you look at the solution. And then you can say, oh, the spectral line of hydrogen is 242 nanometers. And if someone will come and will say, no, in my opinion, the spectral line is 268, then you should answer, your opinion doesn't matter, right? Because we know this, we've studied this, we've spent a lot of time studying so we can understand how this behavior comes about from the laws of nature. But now in our bodies, there are trillions upon trillions of hydrogen atoms, and more complicated atoms like carbons and sulfurs and phosphorus and oxygens. And they all combine to make chemical reactions which are amazingly complicated. And these are combined to make proteins which interact with each other to make very complicated biological structures like humans. And these humans interact to make things which we call societies and communities. And then we have the problem of politics, right? Which is how humans interact. Now, this problem of politics is an extremely complicated problem. But you don't need to learn anything. Everyone can have an opinion about politics, but that is fine. The lesson is that you need to learn and learn and learn, because the more you learn and the more you understand the world around you, the better your opinion is based on the observations. And this is the true bottom line of my talks. So with this, I would like to thank you all for listening and for having me participate in this beautiful, beautiful project. Thank you very much.
Thank you.
You so much, Professor. We have opened the chat for all the students. So if anyone has any questions, you can post your questions there. I have already received a question, Professor. Do you want me to ask that?
Yes, please do, please.
Okay, so the question is from Janani from Villupuram School. She is from 9th standard. She is asking, what is the origin and nature of ultra high energy cosmic rays?
Right. So this is a beautiful question. I'm not a cosmologist by training, so all I know is a little bit about that. But basically, the origin of cosmic rays is the Big Bang. The Big Bang was the process where everything, all matter and energy in the universe were shrunk into a single point. It's not a point in space and time, because space and time themselves were shrunk to a point. That's a hard thing to understand, and I always have trouble understanding it myself. But the idea is that as the world beginning, this point started inflating. And when it inflated, it generated ripples in space and time, like an explosion in air, which generates ripples. This is the explosion. When we hear an explosion in air, these are the ripples in the density of the air that come around us. So cosmic rays are basically ripples in space and time that originate from the Big Bang. Now, one of the amazing questions that people are now asking themselves, and it's very hard to get an answer, is can we combine these physics of the Big Bang, which are essentially classical physics, Einstein's law of relativity, what we call general relativity, and Newton's law of gravity, can we combine them with quantum mechanics? And the answer is, we don't know how to do that. So there's still a lot of things to explain. Things like string theory and superstring theory and supersymmetry are all attempts to explain, to combine these theories of gravity with quantum mechanics. But there is still no theory that does that. I hope I answered the question. Let's have another one. Oh, I can see. Can we time travel in quantum mechanics? Well, the answer is, as far as we know, the answer is no. It has nothing to do with quantum mechanics. In quantum mechanics, time is a parameter, same that it is in classical mechanics. So what we can do is try to understand what time is. Now, that's a very delicate concept. But we do know that according to the law that I mentioned, the second law of thermodynamics, that the arrow of time only flows in one direction. And this means that we cannot go backward in time. Of course, we can go forward in time. That's very, very easy, right? If I just sit here and wait for 2 hours, well, I move 2 hours in time. That's easy. But I can also move in time different than you. Let's recall the last lecture. If I start running very, very fast, very close to the speed of light, time on my clock will go slower. So when I finally finish my jog, I will see that you guys have progressed in time. So it will look like I time traveled to the future. But that's only because time is relative. But you can never go back in time, as far as we know. But maybe we are wrong. More questions. I'm having fun.
Siva?
Okay, there is one more question. Okay, so this is a deep question. I have no idea about this. So let's see. How come the universe is made of matter and not antimatter?
I have no idea. And I think no one does. Okay? So matter and antimatter are really, if you want, different solutions of the Schrödinger equation, or maybe different solution of a more advanced version of the Schrödinger equation, which we call the Dirac equation or the Onsager equation, but it's the same equation. Now they have two types of solutions. In one solution, electrons have a positive charge, and in another solution, electrons have a negative charge. Now, for some reason, our world is composed mostly of electrons which have negative charge. Why is this so? We don't know. Now, let me expand on this a little bit. There are many, many situations in our world where we have a broken symmetry. What is a symmetry? A symmetry is a situation where you change something and nothing should change and nothing happens, right? Let's say you take my hands, right? My hands do not look the same, right? Because they have left and right, right? Look, take your hands and put them one in front of the other, right? They're not the same. One of them is left and one of them is right. They have a reflection symmetry. Very good. I see students doing it. Wonderful. They have something which we call a reflection symmetry. If I put a mirror in front of my left hand, what I will see in the mirror is my right hand. Now, it turns out in the biological systems, there are many, many molecules which have this property. They have chiral symmetry. So do you know something about DNA? DNA looks like a spring. Now, if you have a spring or a screw, it can either turn to the left or turn to the right. But it turns out that in every living thing that we know on Earth, the majority of molecules have a left-sided chirality, although they should work perfectly well with a right-sided chirality. So there is a broken symmetry. Why does this happen? We don't know. And this is the beauty of science. The questions that are unanswered never stop. There is an infinite number of questions that we can answer. In Avengers Endgame, they move past in time. Yes, there's a question by Jay Surya, but yes, but that is a movie. In real life, unfortunately, you cannot go back in time. Let's ask another question.
I don't have any more.
I have another question. You guys, you can ask the questions publicly. So someone asked, what was my dream in my childhood? Did I always dream about being a physicist? No, actually, So my father is a physicist, so I knew the world of physics, but I actually thought for a long time to become an archaeologist, which is a very, very different discipline. But eventually, when I came to university, I, for some reason, decided to be a physicist. So, no, as a child, I did not dream of becoming a physicist, but I hope you do. I hope at least one of you will become a better physicist than I am. More questions? Okay, then.
I think that's all we had. Is there anything, Professor, that you want to say before we end the session?
Yes, well, I just would like to wish you all success in this amazing project, and to the students, study hard, study a lot, and study everything. This is the only way to understand the world around us. Thank you so much for having me in this project. Chaim, thank you.
Thank you very much for coming on behalf of everybody. And let's open the mics so everybody can say personally.
Yeah. So students, you can all just.
Thank you, sir. 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 Thank you, sir.
Thank you.
Thank you so much, sir. Thank you, sir. Thank you, sir. Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir. Thank you, sir. Thank you, sir. Thank you, sir.
Thank you, Professor. Thank you so much.
Thank you, sir.
Thank you for joining. Thank you all.
Bye-bye.
Namaskaram.
Thank you, bye.
Thank you.
Thank you.